Check. Yeah. All right. So basically, this conversation I've been having with you guys tonight is unbelievable. The amount of force and whatever. Once you do the numbers, so just to kind of give an idea for what we're dealing with here, let's say this is your 1 inch by 1 inch tube of water, effectively. Now the weight bearing down on that gives you a certain amount of force at the bottom. This is a square inch here. So how much force is on there? Well, it's just the weight of the water, like 100 inches of water pressing down, and then whatever water weighs, water weight. I was looking that up a minute ago. 0.036 of a pound per cubic inch. So anytime you take that 0.036, multiply it by 100 of those inches sitting above there. Let's say 100 inches. Now you have 3.6 pounds of water sitting in this tube. Now that water per square inch is going to have 3.6 pounds in 1 square inch of pressure at the bottom, as well as 3.6 pounds of force, because it is 1 square inch, right? So now what you've got here is you've got this effectively, I mean, I think you're only going about 80 or something like that. So, instead of 3.6, you're only 80% of that. So times 0.8. So your 2.88 psi is what you have down here in the very bottom section. So let's say you go the first 1 inch going up. You'll actually have for 2.88, let's just call it, times, let's say it's 48 long, 134 pounds of force being exerted along this line at the bottom due to just this lower inch. Now, of course, you then go ahead and add in the next inch, add in the next inch. You can see very quickly you end up with a lot of force that's actually trying to push outwards in this direction, perpendicular to the face of this thing. And that's always pushing in that direction, as well as if you actually draw your dividing line here, over here is exactly the same thing. You have the same force pushing outwards there, so you're doubling that. One's going one way, one's going the other way. You actually have twice that amount that's being picked up by that joint, right? So it's a huge amount of force that you have down there, and I mean, we did discuss the concept of maybe trying to reduce the overall height, which I think would be best if you were to do it. Now, that's your seam issue going on there. You also have the issue of the strength of the perspex itself. I think if we were to come up, let's say, when that perspex blew out, it more or less blew out about a foot high. Maybe it was like a 2 foot by 2 foot kind of section that kind of blew out. So if we come up 24 from there, and then we'll come in 12, and we'll come in 12. So now we've got this little rectangle here of 2 feet by 2 feet that kind of exploded out of it. The water level was up maybe a foot above it, let's say, when the whole thing blew out. So your average depth there is 2 feet. You got your first foot, and then your average depth is bang smack in the middle here. Some of the water is going to be at higher pressure, some is going to be at lower. But let's say you've got this kind of 2 foot mark as being your average. Now, 0.036 per cubic inch per basically inch of height. So we've got 2 of those, so times 24. That means that from there down to this point, you've got this 0.86 psi on average acting on this square. Now that 0.86 psi, when you multiply that by 24 times 24 to get the actual force times 24 times 24, there we go. So 500 pounds is how much force is 500 pounds is how much force is acting, because you kind of had this thing kind of bolted in there and bolted there and bolted in a few places along the bottom, but this kind of free space in the middle, assuming you only got it filled up that high, is already 500 pounds of force pushing on that thing, which is, a pretty crazy amount of force. Now that you know, with the stresses of maybe, a hole being drilled in it, weakening in one particular spot, it looks like it just kind of wants to shear along there, which makes sense with that 500 pounds pushing directly outwards. You got a couple of three big guys kind of thing standing on it almost. Yeah, what do you do about that? Well, very good question. Maybe there's not a lot you can do. I mean, yeah, you could go thicker with the stuff for sure. You could bring down your height. Let's say you're only coming down now to that 4-foot magic height. Well, now you've just reduced your maximum pressure here to just, not much past 1 psi at the bottom. That's definitely something that will help a lot. Another problem that you have, if you were to do that, you still really need to make sure that you're not going to end up with a big 2-foot by 2-foot that's free and clear 1 foot below the surface, the top level, because that's potentially going to blow out your perspex anyway. So a way to avoid that is if you have, let's say you come up 1 foot, that's 1 inch, 12 inches there, and you're going to have your little rectangles, maybe just in like that and like that. Well, what you're doing now is you're effectively picking up all of this force that's in here is now going to there, and this stuff here is going to there. So you've got a much smaller area going on there. That's sort of, that cumulative area is what's killing you. Like, there's no problem if this was just a really small cylinder like this with the 3 pounds per square inch going on. You could take up that 3 pounds no problems if it was like fully locked in all the way around and you only had like 3 pounds going on, that's it. But as soon as you start adding 3, 6, 9, 12 and then all this sort of area here, that's what's fucking you up. So yeah, I mean, depending on what's going on with the bubbles, like, you're just looking to try to eliminate that clear span as much as possible. A really good thing that you could do, like I do, that whole concept of maybe coming in with some perspex on the side, 4 inches, let's say, put the perspex down on the nice flat side and then come in like that. Well, part of what you've done there is you've just eliminated that clear span down to 3'4" from 4 feet, right? So you're bringing in that total area that's able to push, which is fantastic. You've also increased, obviously, your gluable surface area here, so that's now able to take more force. And then if you were to bring, a little something in there, like that's just going to do something like that, well, again, your distances now have closed down. You've got less than a foot there. Well, that just might be enough. But this is your trouble area down here, though. Like, by the time you get up here, you're probably fine to do something like that, sure. But this down here is definitely going to be the area that's going to cause you the difficulty. And, if you got to go 5 inches up from the bottom, just to try to get a little bit more gluable area, have that running all the way along, and then your piece here, sort of comes down and sits on top of it, just to try and give you that strength that's continuous all the way along the bottom. You're dealing with kind of uncharted territories here as usual, but I mean, that's really all that I can think of. Like, I'm shocked by those numbers. I didn't think for a minute that perspex would blow out. You'd have a problem with that, but if you run the numbers, they are what they are, and unfortunately, those forces that you're having to contend with are absolutely huge. By having that kind of 80 inch or whatever it is right now, total height.